Hello everyone and welcome to the 9th lecture of the course Advanced Structural Analysis. We have briefly discussed the basic concept of the stiffness approach in the previous session. We introduced the idea of the general stiffness coefficients and we looked into the problem from the general context of the simple indeterminate system. Now, as we move ahead with this session, we try to identify the problem of the truss systems, which we will also like to solve using the simple flexibility approach. Now, the intention of this session is to cover the problems related to the truss members using the flexibility method. Then we also wish to include the inclusion of the support yielding or the support rotations, which are typically the cases of the support settlement in the given system, and we want to see this from some of the example cases. As we have discussed earlier, these are the basic steps which are typically used in the force method. Just to have a brief recap, we understand that we considered the system as the statically indeterminate system at the beginning. We evaluate the system's static indeterminacy, say the value appears to be n, and then corresponding to those n number of extra support reactions or the internal member forces, we remove them and we convert the given system into a statically determinate and stable system. So, a stable and the statically determinate system is considered as the initial system on which we reduce all the given considerations. Once we have identified the system, which is a release system, we subject the given system to the external load provided in the original problem, and we calculate the amount of deformations in the direction of these redundants which has been selected in the step number 2. So, one important aspect of the force method is that one not need to look for the steps in the subsequent manner by remembering them, but one can easily understand that as we are converting the given system from an indeterminate system to a determinate system, we are removing some number of reactions or the internal member forces of the given system. These are all called as the redundants, and once the redundants are known to the given user, we look for the given compatibilities in the direction of these redundants only to be satisfied. So, in order to do so, we evaluate on the released system the amount of the displacements in the direction of the redundant, that becomes our component delta L. Then one by releasing or applying the individual amount of the redundant values, we calculate the displacements again in the direction of all the redundants with respect to the redundant forces. So, corresponding to the redundant number 1, we calculate the application of the load and we calculate the displacement in the direction all the given redundants of the problem. Similarly, we do it for the amount of the redundant force in the direction of the redundant 2 and calculating the displacement in the direction of all the other redundants, and by doing so we are able to identify the amount of the displacements in the direction of the redundant due to external load as well as the redundant system. Finally, we define the net compatibility conditions, which are the delta equal to delta L plus the delta R, and this delta R component is nothing but it is the representation of the flexibility matrix into the individual values of the redundants. As we are considering that the given system is represented with respect to a large scale system having multiple redundants, so we describe the flexibility not as a single coefficient, but a multiple flexibility coefficients of the given system, and the redundant R also becomes a vector containing all the redundant forces of the given system. These will be appearing as a n number of n number of compatibility conditions of the given system, same as the original number of the static indeterminacy or the selected choice of the redundants of the given problem, and by solving these linear set of equations, we evaluate the system's unknown redundants of the given problem. Once we evaluate these unknown redundants, we can go ahead with the calculations of the system's other unknown parameters of the given problem. Okay. As we have seen the application of the simple flexibility method to the standard beam problem, with this session we would like to see the standard truss problem and try to analyze them using the flexibility approach. As initially we are given a problem in which we have considered that there is a load which is applied at the point C. The system is subjected to some conditions of the support conditions. As we consider the degree of static indeterminacy, we go with the same idea which we initially defined. We can identify the degree of static indeterminacy as the total number of unknowns, which are the unknown set of reactions of the given system. We have total 1, 2, 3 and 4 number of reactions appearing in the given problem. We define them as R1, R2, R3 and R4 for the given system. And out of all these set of available reactions of the given problem, we consider now that the given system internally will also be having some indeterminacy in the problem. For that, we identify the total number of members which are responsible for identifying one unknown force in the given system, minus 2 times the number of joints in the problem which are identifying the available equilibrium equations in the given problem. By doing so, I get the R, which is 4, the number of members in the given system which are 6 in the given system, and the number of joints which are 4 in the given problem. So, this gives me a overall condition of the static indeterminacy as 2 for the given problem. Once we know that the system is having a static indeterminacy of a 2, one can also do this and calculate that the degree of static indeterminacy for external system appears to be 1, which is 4 number of total unknowns in the given problem minus 3 number of equilibrium equations in the given problem. It is important to understand that the equilibrium equations for the overall system are considered the summation of the forces along the direction x equal to 0, summation of the forces along the direction y equal to 0, and at the same time the net moment of this given system should also be 0, so that the overall structure does not undergo any kind of a free rotation. So, having these 3 conditions applied for the external system, we get the degree of external indeterminacy as 1. Using this, we can also calculate the internal indeterminacy, and that comes out as the number of members as the unknown, which is 6, and the remaining number of equilibrium equations available for the given system. So, 2j is the total number of equilibrium equation, out of which 3 has been utilized for the external system. So, we get only 1 as the degree of internal indeterminacy for the given problem. So, what we realize now that we can consider this problem, convert it into the statically determinate problem by removing one external reaction and one internal member, so that the indeterminacy for the internal and external system both can be removed from the given problem. As a one possibility of the given system, we consider that this is a determinate system in which we have removed this member and we have also removed the reaction at the support D. And as we have removed these 2 conditions, this is though the original released structure of the given system subjected to the external load, but at the same time this is not the same problem as the original problem given to us. So, we have to consider the similar system with the redundant value of R1, which is corresponding to the given reaction at the point D applied to the given problem, and then at the same time the second member force which is considered or which is removed from the original problem, its internal force also is released, and that is considered as R2 in the given problem. And now we say that the addition of these three systems together will be giving us the net system which is originally defined to us. So, this is the system of the redundant 1 and this is the system of the redundant 2. Just to remove the confusion out of it, we will not consider these reactions as R1, R2, R3 and R4. We can later define these values, but initially we had 4 number of reactions, we did not label them, but the redundant values have been labeled as R1 and R2 in the given system. One important aspect which we define over here, that typically the redundants have been defined in the direction of the positive coordinate. So, at the point D, the support reaction D is considered, and we have considered this in the positive x coordinate. Similarly, when it comes to the internal member forces, we consider most of the times the tension force in the member being positive, and with that idea we have considered if the member will be in tension, the ends of the given support will be subjected to the given set of forces, and these are the forces which have been released at the 2 ends of the given system, which are this end B and C of the given system. So, we have considered the positive set of reaction system for the redundants of the external load external reactions, and the tension being positive is considered for the identification of the positive redundant force component in the given system. Now, as we define the given conditions and we have defined the choice of the redundants of the given problem, we move to the step number 3. Now, as a step 3, we identify first the amount of the deflection in the direction of the redundants due to the external load, which typically means that this is the system due to the loading, and in this system we want to calculate the displacement in the direction of the redundant one, which we call as delta 1 L, and also we want to calculate the displacement in the direction of the redundant 2, which we call as delta 2 L for the given problem. Of course, delta 1 L is the horizontal displacement of the joint D, whereas delta 2L is the relative displacement between the joint B and C of the given problem. In order to define these values, we understand that this is a statically determinate system. We can use the standard methods of the statically determinate system to calculate these values. Now, in order to calculate first the delta 1 L in the given system, we realize that we can use the energy theorem. If I want to calculate the value of delta 1 L in the given system, I must have a unit load at this given point, and that can be provided by this given system, which is already available to us. So, I can consider that this is the real system and this is the virtual system when I am looking for the calculation of delta 1 L in the given problem. The external work done can be calculated as half, and as it is a virtual system, so I will not be keeping the factor of half, and I will define the R1, which is the external load considered with the 1 unit value. So, R1 into the amount of displacement over here, which is delta 1 L in the given problem. And this external work done should be equal to the internal strain energy associated with these two given systems. Now, if we recall the expressions of the internal strain energy, we can realize that the strain energy associated with the truss members was already written as S1 S into dx upon EA for the given system, and this is defined with respect to the integral sign. But as we understand, the internal forces in the truss members are constant all throughout, so I can directly write this expression as summation for I equal to 1 to m for all the members, and this can be simply written as Si into S, and instead of the dx I can simply multiply it with the length of the member into AE. So, this expression can typically give us the standard value of the internal stored energy of the given problem. Now, once we equate both of these values, I get that the value of the delta 1 L in the given problem is identified as summation for all the member 1 to m, and now S of I, as we are looking for the deflection in the direction of the redundant one, it should be with the expression of S1 in the given system, S into L AE in the given problem. Now, what we understand that S1 happens to be the internal member forces in each of the members corresponding to the unit load applied at the position of the D. So, this is a system of S1. Similarly, the S, which is the external load system of the given problem, is the system over here. We calculate the internal member forces in each of these members due to the external load, and that is what defines the S as a representation of the given system. This need to be done for all the members, and that is why we have done the summation for all the members 1 to m in the given case. In the similar manner, if I want to calculate the delta with respect to the second redundant, I will define it as delta 2L, and that can be described as summation I equal to 1 to m S2 S L upon AE. So, this could also be described with respect to the system, where now S2 represents the internal member forces when we apply the unit load in the direction of R2, and corresponding to that we have all the member forces being evaluated. Multiplying them with the loading system, I can calculate the overall displacement in the direction of the redundants due to the external load. Now, the similar process we can do for displacements in the direction of the redundants due to the redundant forces itself. So, in this case, when we start with the calculation, we consider that as a first case we have the system of R1 in which we are applying some unit load, and corresponding to this I am looking for the displacement also in the same direction. Say that value of the displacement is being called as the f of 1 the flexibility coefficient 1, or we can also call it as delta in the direction of the redundant 1 with respect to the redundant 1 of unit value. I can also calculate with respect to the unit value of this given redundant force, and I can calculate the relative displacement between these 2 points, and that can be described as delta in the direction of the redundant 2 with respect to the unit value of the redundant 1, and this can be described as f of 2 1 in the given system. So, now in order to define these values of f of 1 1, f of 2 2, we can consider the similar system of the virtual work principle. We can consider that as a generalized system, if I am applying the load in the ith direction of the given system, and corresponding to that I am calculating the deformation in the jth direction of the given system, I can calculate it as the original system. Say one of the system could be considered as a real. I am doing the calculation for f of 2 1, but the same can be extended to the calculation of f of 1 1 as well. So, I am considering that this is the real system and this given system is the virtual system. So, as we are applying the unit load in this given system and I am looking for the displacement in the direction of the redundant 2, I am considering that in the direction of the redundant 2 having a unit load is my virtual system. Now, corresponding to this, the work done or the virtual work done of the given system will be equal to 1, which is the amount of the force in the direction of R2 in the virtual system, into the amount of the displacement in the real system for this, which is delta of 2 with respect to the R1 being 1 unit in the given problem. And we can describe this value as f of 21. So, I can directly call this as f of 21 for the given system. Corresponding to that, I can define the strain energy associated with the given system. And now, if I go with the strain energy expression in the similar manner, I can define it as I equal to 1 to m summation for all the members, then S1, which is reflected with respect to the virtual system. So, it will be S2 for the present case, into the expression with respect to the original system, which is S1 and the length of the member into AE. So, this is the expression which we typically define for the strain energy of the given system, provided that we are considering this system as a virtual and this system as a real system. I can do the similar calculations for the remaining flexibility coefficients of the given problem, and by doing so we can define that the standard expression can be written for the given system in this manner, where delta in the position of the redundant 1 in the original system can be calculated, and this will be the sum of delta due to the external load system, delta due to the redundant value 1, which is described over here as f of 1 into R1, and delta again in the direction of 1 with respect to the redundant 2, and that is described as f of 2 into R2 in the given system. So, taking the sum of all these three values, I can write the first condition of the compatibility, and that is described over here. Similarly, when I go to the condition with respect to the relative displacement between point C and B, we realize that it is the sum of the displacement with respect to the load system. So, it is delta 2 with respect to the load. Then similarly, over here we define the corresponding displacement in the direction of the position, relative position of point B and point C. This could be defined as delta in the direction of 2 with respect to the redundant R1, and we have described this as f of 1 into R1 in the given problem. And then finally, we describe this value with respect to the second redundant, and that value comes out as f of 2 into R2 for the given system, and this will be the delta 2 with respect to the R2. Now, finally, we add these all contributions together, and this becomes our second compatibility conditions. As we have already seen that we can evaluate the individual coefficients of the loading components as well as the flexibility coefficients by writing this standard form. We have these expressions available to us, and now we describe a standardized table in which we calculate corresponding to the external load system. We call it as a system S. So, we calculate all the member forces, and those are described with respect to the given loading. Then we come up with the system which is S1 corresponding to the redundant 1 being 1 unit, and we describe all the forces inside it, those are also described in this manner. And then we come to the redundant 2 system and describe all the member forces in the given system, and those are described as a S2 components of the given system. We are not going into the solution of these systems, considering that these are statically determinate system. You can follow the regular methods of the truss analysis, either a standard joint equilibrium method or the section method, and through that you can calculate all these member forces. While writing these forces, we have considered that members which are in tension, those are considered with the positive forces, whereas the members which are in compression have been defined with the negative forces. Now, as we get the expressions in the previous case, we evaluate these individual components of the given system, and as we need to do the summation of all these components for individual members. So, we are doing this calculation such that we have all the members lined up, and for all of these members we define the values of L and AE parameter, and then we also evaluate the individual values of S, S1 and S2, and through that we evaluate these individual coefficients. So, once we do that for all the members and take their summation together, we generate these expressions which are the summation for all the members and the summation of S1S L upon AE, summation of S2S L upon AE, and subsequently the remaining flexibility parameters. Now, using this parameter, we go to the compatibility conditions as we have defined. We have written already these expressions for the given system in this manner, and by using the previous defined conditions of the table, we can give them the numerical values, and through that we can evaluate the reactions of the given system. So, these are the reactions which can be evaluated for the given problem, and these are the reactions or the redundant values of the given system which initially we identified. Now, as we move with this part, we understand that the first step of the analysis has considered the loads active on the given system, but at the same time we have not considered some of the secondary criteria which typically appear in the given problem. One of the secondary criteria which typically appear in most of the structural cases is the possible movement of the support in the given problem, which means that if we have, say, a support and it moves by some value of delta from its position, then what is the influence of that given system on the overall system reaction. Now, one basic difference between the statically determinate and the indeterminate system can be understood. That is, if we have a statically determinate system and we have a possibility of one deformation taking place in this manner, then as we understand that the rotation is free to take place at both the systems, the system support will move from this position to this position and the members will simply deform in this manner. Deform in the sense like the system will have a free rotation which is taking place and the member is not undergoing any kind of a internal deformation. So, a very much advantage with the determinate system is that any kind of a support movement does not introduce internal forces in the given system, and this is much more easier to solve, but at the same time we realize that the indeterminate systems are the primary and the preferred systems for the analysis, due to a very simple reason that if I just give only one support or the necessity condition of the equilibrium for the given system, any of the possibility of, say, failure at one support may lead to the overall failure of the given system. To avoid it, typically the engineers or the civil engineers rely upon the practice of introducing more number of supports in the given problem, and that introduces the static indeterminacy in the given problem. But the moment we have now the statically indeterminate system and we apply the similar set of deformation in the given problem, now no longer the system can freely deform. One can understand this in a simple manner like this, that as the support has moved from this position to the new position, and say with respect to this part the system wants to deform, even though there is a possibility of the rotation to take place over here, the system cannot be considered with respect to the system which is deforming over here has to maintain the slope in the second part as well. So, the system will undergo some part of the deformations in the successive remaining portions also. So, this will be the typical deformation which the system will undertake, and with this parameter we understand that as the members have undergone deformation, there will be stresses and there will be reactions which will be generated all throughout the system, even though the system is undergoing a simple support settlement. This could be considered largely for the system as a general case where we have provided at the end of the support some rotation as well as some deformation in the given system, and this can result into a simplified profile where the system has undergone a deformation and it shows that the member of the beam which was initially straight has undergone some deformation, and as the deformation has taken place in the given system, there will be some internal forces which will also be accounted in the given system and they need to be considered. We can also consider a simple case of a truss like over here. It is a indeterminate problem in which if any of the members say undergoes any length change, say this given member BD has some change of the temperature due to which the length changes. Now, these change of the length will also result into the relative changes in all the other members, and that will result into the external support reactions as well as the internal member forces of the given system. Whereas, if we consider the same problem with only the determinate part of the given system, say a system having these supports and only one particular member being defined like this, I can consider that the given system or one of the member say have some of the temperature changes, but these temperature changes may simply be taken care by the general deformation of the members without influencing the overall distribution of the forces in the given system. So, a determinate system undergoing any kind of such changes may not introduce any kind of forces in the remaining members or the remaining supports of the given system, whereas an indeterminate system under the influence of these secondary forces undergoes the full deformation of their span as well as the reactions and the other criteria will appear in the given problem, and that need to be accounted. In order to define them, there are two approaches which typically we take. The very first approach is we consider these changes in terms of the support settlement or in terms of the member length change due to temperature or any other criteria as the compatibility conditions of the given system. So, if I say that the support D over here has a possibility to move in the horizontal direction by some value of say 2 mm, I can consider that this criteria of the delta is added in the initial compatibility condition itself of the given problem. At the same time, if I say that, say one of the members, say BC of the given system is say little shorter than the original length which was anticipated for the given system. So, that can also be accommodated as the possibility of the compatibility condition for the given system, where the relative displacement between the joint B and joint C can be defined equal to the amount of the length by which the member is short or longer. And this idea can be reflected as a simple case where we say that the delta 1 and delta 2, which is the primary criteria of the compatibility, can now be accounted by these parameters of the support yielding or member length change. So, in a cases where the criteria of the support settlement or the member length change are accommodated in the same directions in the directions of the redundants, we can consider them directly. So, delta 1 over here can be considered directly as the available set of displacement which is available in the direction of the given redundant 1. In the similar manner, the system of the relative displacement between the joint B and C can also be considered as the criteria of delta 2 for the given system. With this idea, I can consider that if the support moves in the horizontal direction by 2 mm, say in the positive x direction, I can consider delta 1 as 2 upon 1000, that is the dimension in the meter, and that is the value which we need to describe for delta 1. Earlier we were taking this value as 0, considering that the support does not move. In the same manner, if I consider that the member BC is shorter than the original length by 2 mm, which means that if the member 2 mm is shorter, that means it will be under tension, and that is what will also give me the positive set of force in the given system, and that can be reflected by 2 upon 1000 for the given system. Right. So, based upon the criteria of the given conditions which are in the directions of the redundant, we can directly add those conditions in the compatibility of the given system. So, we can add now these criteria and say that instead of 0, this value comes out as 2 upon 1000, whereas this value, if it is 2 mm shorter, it comes out as 2 upon 1000. If it is 2 mm longer, that means the member will be under compression, and that can be defined as minus 2 upon 1000 for the given system. So, with this idea in mind, we can include the conditions of the support settlement or the member length change as a one simple criteria as a compatibility condition. We do a second case in which we have a given beam subjected to the support settlement at the end B, which is the vertical settlement of delta and the rotation of the given support at the B as well. Now, this is a very standard problem which we take as the base problem for the displacement method. That is why we want to look this problem over here, and if we consider this problem, this is the deflected shape typically which we introduce. Now, how do we solve this given problem? As we said that one simple way of solving this support settlement is if we consider these values itself as a in the direction of the redundants of the given problem. So, what a user can do, user can consider that the determinate system of the given system or the release system is provided such that the reactions over here itself are the redundants of the given problem. So, I will now consider this cantilever beam as a simple release structure, and the first reaction in the direction of the delta is considered as R1, and the second redundant in the direction of theta is considered as R2 for the given problem. And now I can simply write the condition of the compatibility that the delta 1 is equal to, which is in the direction of the redundant 1, is equal to the delta 1 due to the redundant due to the release system due to the external load, delta 1 due to the R1 active on the given system release system, and delta 1 due to the R2 active over here in the given problem. And once I add the cumulative sum of these two values, I will now describe the condition of delta 1 and theta 2, which are at the joint B of the given system, as the compatibility conditions of the given system. So, as I realize that delta 1 is in the downward direction, which is opposite to the R1, the choice of the redundant which has been selected. So, I define that this compatibility is minus delta, whereas theta is in the same direction of the redundant which is selected. So, I define this as theta in the given problem. As we describe further the values, there is no loading active on the given system. So, delta 1 due to the load is 0, delta 2 due to the load is also 0. Now, I can define the values of f of 1 1, f of 2 2, f of 2 1 and f of 2 2 using the same idea which we did earlier, and in that case we can consider that these expressions will be similar as we consider a simple problem where we have the redundant 1 and redundant 2, due to which we describe the moment distribution with the values of m1 and m2. And now I can consider that f of 1 1 is simply the criteria of m1 m1 into dx upon ei for the given problem. Similarly, f of 2 1 or f of 1 2 is m1 m2 dx upon ei for the given problem, and finally f of 2 2 is m1 m2 m2 dx upon ei for the given problem. And using these criteria of the moment distribution, we can evaluate these expressions for the all four flexibility coefficients of the given system. Once we evaluate these values, we describe these values over here, substitute the conditions of the compatibility, that with respect to the delta 1 we have a compatibility condition equal to minus delta, with respect to theta 2 we have a compatibility condition equal to theta, and by solving it we can get the values of R1 and R2 in the given system. So, once we solve these values of R1 and R2, we get that these values are standard values which we typically define. Now, if one just simply wants to describe this as a two separate case, we can easily understand this as that in a standard case, if the system at one of the support B undergoes some rotation of the value theta, there is a moment which is generated over there which is of the amount 4 ei theta upon L. The far end also gets a moment reaction which is 2 ei theta upon L. At the same time, due to these two reactions or the two reactions of the moment, now we get both in the same directions, we get the net reaction of the given system which is 6 ei theta upon L, and we need to balance this reaction of the moment by the opposite moment couple, and this moment couple in the opposite direction can be generated by two equal and opposite forces like this. So, we have provided one reaction here upward, one reaction here downward, and this reaction should be equal to the amount of moment divided by the lever arm length of the given system. So, this is 6 ei theta upon L square. These are the reactions defined for the given system. In the same manner, we can describe this second case also, in which we have only the delta taking place in the given problem, and with respect to this delta we evaluate the system and we get these reactions as 6 ei delta upon L square over here in the second case, and then corresponding to that we can calculate these reactions as well, which appears as 12 ei delta upon L cube. These are the standard results which we typically consider when we go ahead with the displacement method, and these are the results which are typically based upon the force method are realized, and we consider them for the further analysis. With this we stop over here. We have briefly discussed the standard results in the deflections of the beam profile. We have included the deformations which are taking place at the supports, and we have considered them as a standard compatibility conditions in the given system. Now, there may be conditions where the given support settlements or the member length change are not in the direction of the same redundants, and in those conditions we need to again accommodate that, which we will see in the next lecture. Thank you everyone.